The universe is a vast and mysterious place, filled with wonders that stretch beyond our imagination. It is governed by laws of physics that shape the cosmos, dictating the movement of galaxies, the formation of stars, and the behavior of particles. In our quest to unravel its secrets, we often turn to the language of mathematics, a universal tool that transcends cultural and linguistic barriers. Mathematics is a powerful tool that allows us to describe and predict the behavior of everything from celestial objects to subatomic particles, providing a framework for understanding the universe. One such mathematical marvel that plays a pivotal role in our understanding of the cosmos is the mean value theorem, a fundamental concept in calculus. This theorem, a cornerstone of calculus, provides a profound connection between the average rate of change of a function and its instantaneous rate of change at a particular point, bridging discrete and continuous analysis. Imagine a car cruising along a highway, moving smoothly through the landscape. If we know its average speed over a certain distance, the mean value theorem tells us that at some point during that journey, the car's speedometer must have displayed that exact average speed, even if just for an instant. This deceptively simple concept has far-reaching implications, allowing us to bridge the gap between the macroscopic and microscopic worlds, from the vastness of galaxies to the minute details of cellular structures. It provides a glimpse into the intricate workings of our dynamic universe, revealing patterns and behaviors that might otherwise remain hidden. In the realm of astrophysics, for instance, the mean value theorem helps us analyze the motion of celestial objects, such as stars, planets, and comets. By knowing the average velocity of a planet over a specific time interval, we can determine the exact moment when its instantaneous velocity matched that average, a crucial insight for understanding orbital mechanics. This ability to connect average and instantaneous rates of change is crucial for understanding the orbits of planets, the paths they trace through space, and the forces that govern their motion. It also sheds light on the expansion of the universe, helping us comprehend how galaxies move apart and the rate at which the cosmos is growing. Furthermore, it aids in understanding the behavior of black holes, those enigmatic regions of space where gravity is so intense that not even light can escape. As we delve deeper into the intricacies of the mean value theorem, we will uncover its elegant logic, its profound implications, and its ability to simplify complex phenomena. Its wide-ranging applications in various fields of science and engineering demonstrate its versatility and importance, from designing efficient algorithms to optimizing engineering processes. So, fasten your seatbelts as we embark on an exhilarating journey into the heart of calculus, where the mean value theorem awaits to unlock a universe of knowledge and understanding. Join us as we explore this remarkable theorem and discover how it continues to illuminate the mysteries of the universe, one equation at a time. Before we dive headfirst into the depths of the mean value theorem, let's take a moment to appreciate the brilliance of its predecessor, Rolle's theorem. This theorem, though often overshadowed by its more famous counterpart, holds a special place in the world of calculus and mathematical analysis. Named after the 17th century mathematician Michel Rollet, this theorem serves as a crucial stepping stone towards understanding the more general mean value theorem. Michel Rollet, a prominent figure in the history of mathematics, contributed significantly to the development of calculus, and his theorem remains a fundamental concept taught in classrooms around the world. In essence, Rollet's theorem provides a specific case of the mean value theorem, laying the foundation for its more expansive implications. It is a beautiful example of how a simple idea can lead to profound insights and applications in various fields of science and engineering. Imagine a roller coaster on a track, starting and ending at the same height. This visual analogy helps us grasp the core idea behind Rollet's theorem. Rollet's theorem tells us that at some point during the ride, there must be at least one point where the roller coaster comes to a momentary standstill, its instantaneous velocity dropping to zero. This point of zero velocity is crucial for understanding the behavior of the roller coaster and, by extension, the function it represents. This intuitive concept, while seemingly simple, has profound implications for understanding the behavior of functions. It allows us to predict and analyze critical points where the function's rate of change is zero, which is essential for various applications in physics, engineering, and economics. Mathematically, Rolle's theorem states that if a function is continuous on a closed interval, a, b, ensuring that there are no breaks or jumps in the function's graph, differentiable on the open interval, a, b, meaning the function has a well-defined tangent at every point within this interval, and fa equals fb, indicating that the function takes the same value at the endpoints of the interval. Then there exists at least one point C in AB, such that fc equals 0. This point C is where the function's derivative or instantaneous rate of change is 0. In other words, if a function takes on the same value at 2 points, then its derivative must vanish at some point in between. This result is not only elegant, but also incredibly useful for solving real-world problems. Rolle's theorem might seem self-evident when visualized as a roller coaster ride or a smooth curve, but its mathematical formulation provides a rigorous framework for analyzing the behavior of functions. This rigorous approach ensures that we can apply the theorem confidently in various scenarios. It guarantees the existence of a point where the derivative is 0, a critical piece of information for finding maximum and minimum values, analyzing the shape of curves, and understanding the dynamics of physical systems. This guarantee is invaluable for mathematicians and scientists alike. As we move on to the mean value theorem, we will see how Rolle's theorem serves as a crucial building block, providing a special case that illuminates the more general principles at play. The mean value theorem extends the ideas of Rolle's theorem to a broader context, offering even more powerful tools for analysis. The relationship between these two theorems highlights the interconnectedness of mathematical concepts, where seemingly simple ideas can unlock a deeper understanding of complex phenomena. This interconnectedness is a testament to the beauty and elegance of mathematics, where each theorem builds upon the previous ones, creating a rich tapestry of knowledge. With Rolle's theorem firmly under our belts, we can now venture into the more expansive realm of the mean value theorem. This journey will take us deeper into the heart of calculus, revealing more about the behavior of functions and their rates of change. This theorem, a cornerstone of calculus, generalizes the concepts introduced by Rolle, extending its reach to encompass a wider range of functions and scenarios. It builds on the foundation laid by Rolle's theorem, offering a more versatile tool for analyzing functions. While Rolle's theorem focuses on functions that have the same value at their endpoints, the mean value theorem broadens the scope to include functions with different values at their endpoints. This expansion allows us to apply the theorem to a greater variety of real-world situations. Imagine driving along a highway with varying speed limits. The road may twist and turn, and the speed limits may change, but the mean value theorem provides a way to understand our journey in a new light. The mean value theorem tells us that at some point during our journey, our instantaneous speed must have matched the average speed calculated over the entire trip. This insight can be incredibly useful for understanding motion and change. This means that even if we speed up or slow down at different points, there will always be at least one moment where our speedometer reading aligns perfectly with our average speed. This concept is not just limited to driving, it applies to any scenario involving rates of change. Mathematically, the mean value theorem states that if a function f is continuous on the closed interval, aab, and differentiable on the open interval, aab, then there exists at least one point C in AB such that fc equals fb minus fa divided by b minus a. This formal definition provides a precise way to identify the point where the instantaneous rate of change matches the average rate of change. In simpler terms, this means that the instantaneous rate of change of the function at CE is equal to the average rate of change of the function over the interval a, b. This relationship is fundamental to understanding how functions behave over an interval. The mean value theorem bridges the gap between Rolle's theorem and a more general understanding of functions. It serves as a crucial link, helping us transition from specific cases to more general principles. It tells us that even when a function doesn't necessarily start and end at the same value, there's still a point where its instantaneous rate of change mirrors its average rate of change. This insight is powerful, as it allows us to make predictions and understand the behavior of functions in a broader context. This connection between the local and global behavior of functions is a testament to the power of calculus, allowing us to glean insights into the overall behavior of a function by examining its instantaneous properties. By understanding these principles, we can better analyze and predict the behavior of various systems in mathematics, physics, and beyond. While the mathematical formulation of the mean value theorem provides a rigorous framework for understanding its implications, a visual representation can often illuminate its essence more intuitively. Imagine a graph depicting a smooth curve representing a function over a certain interval. The mean value theorem tells us that there exists at least one point on this curve where the tangent line is parallel to the secant line connecting the endpoints of the interval. This geometric interpretation provides a clear visual representation of the theorem's central idea. The secant line represents the average rate of change of the function over the interval, while the tangent line represents the instantaneous rate of change at a specific point. The mean value theorem guarantees the existence of at least one point where these two lines are parallel, signifying the equality between the average and instantaneous rates of change. This visual representation helps us grasp the essence of the mean value theorem beyond its mathematical formulation. It allows us to see how the theorem connects the local behavior of a function at a specific point to its global behavior over an entire interval. The parallel lines serve as a reminder that even amidst the complexities of a function's curvature, there exists a point where its instantaneous rate of change aligns perfectly with its average rate of change.